Good day, everyone. Here's part 7 of our discussions on nuclear chemistry. So for this video, I would be describing the induced nuclear reactions. So these are special types of nuclear reactions. Tell about nuclear fission and some of its applications. Tell about nuclear fusion and some prospect for the barriers to its use for the production of energy. Let's start our discussion on induced nuclear reaction. So one such reaction is called artificial transmutation. So these are just man-made nuclear reactions. So nuclear reactions can occur if a particle collides with the nucleus. So just like what happened in the formation of carbon-14 isotope, a neutron bombarded an atom of, or the nucleus of an atom of nitrogen and converted it into nitrogen-14. So Rutherford, a long time ago, produced the first transmutation. Instead of a neutron, he made use of helium or alpha particles to bombard the nucleus of nitrogen. So he was able to produce oxygen-17 isotope and a hydrogen atom. But alpha particles are not ideal. Positive particles are hard to insert into a positive nucleus because they would be repelled by the nucleus. So artificial transmutations for the neutrons work better because neutrons are neutral particles. They will not be repelled by the nucleus of the atom being bombarded. So many elements are synthesized in this way. So the elements that you can find in the bottom part of the periodic table are mostly synthesized through artificial transmutation. So for example, the nucleus of plutonium-239 when bombarded with a neutron, these are fast-moving energetic particles, is converted to plutonium-240. And then, when plutonium-240 is bombarded by another neutron, it is converted into an isotope of plutonium still. And then, the radioactive plutonium-241 isotope that is formed disintegrates into americium-241 and the release of beta particles. So this is how americium was developed. It was not discovered. It was developed and synthesized in a nuclear laboratory. So nuclear fission is another special nuclear reaction. So this takes place because of the bombardment of uranium-235 by a neutron, resulting in the formation of a daughter isotope uranium-236, which is likewise radioactive, and it disintegrates to form the daughter isotope barium-141 and krypton-92, and the release of 3 more neutrons. So 3 more neutrons are produced, and these neutrons are used to fire at other uranium-235 isotope. So the reaction goes on and on and on, and this is said to be a chain reaction because each bombardment produces further greater number of neutrons. So the reaction is very exothermic. It produces up to -2. So -2 means it's exothermic, 2 times 10 to the 10 kilojoules of energy. Now let's talk about nuclear reactors. One very important, huge application of nuclear power is in nuclear reactors. So thermal energy from fission is used to generate power in nuclear reaction. So the control rods are neutron absorbers. So these are cadmium, boron, and they keep it under control. So if it works by fission, that means to say neutrons are used to bombard uranium 234. There. Uranium oxide pellets are in the fuel. The chain reaction is started by a neutron source, and the neutron source is the helium, or this is beta, bombarding beryllium. So beta is produced by the disintegration of plutonium into uranium-234. So the beta particles produced are used to bombard beryllium to produce the neutron. So natural uranium is 99.3% U-238. U-238 is not fissile. That means to say, this isotope, although it is radioactive, does not undergo fission. So it's not possible for it to be bombarded by neutrons. So reactor fuel rods are enriched up to 2-3% of uranium-235. So uranium-235 is very fissile. That means to say its isotopes can easily be bombarded by neutrons. So for weapon grade uranium, these are the ones being used in nuclear warheads. The presence of uranium-235 there should be greater than 90%. So there. So it's so dangerous. Nuclear warheads. So this is the diagram of what is inside the nuclear reactor. Nuclear reactors look like this. Towers emitting steam because the energy generated by nuclear reaction is used to convert water into steam, and the steam is used to run the turbines, which in turn works on the generators to produce electricity. So it's clean, it doesn't produce carbon dioxide, but it produces a lot of radioactivity. So inside the core of a nuclear reactor is the containment structure. So this is where the fuel rods are. This is where the uranium rods are placed. It is insulated from the rest of the world by a thick layer of concrete and lead, and energy is generated here. So there are pros and cons to the operation of nuclear reactors. So the Philippines is trying to have one, planning to have one in the future. So these are the pros and cons. Nuclear power plants produce clean energy because they do not produce carbon dioxide that is emitted to the atmosphere. But they yield highly radioactive waste, tens of thousands of tons in storage. So long half-lives of plutonium-239 so that would be 24,400 years. So even if a nuclear power plant is shut down, there would still be remaining radioactive isotopes scattered all over the place or within the vicinity for a long, long period of time. It can be vitrified or encased in glass, actually. No? Those that remain after the operation can be vitrified or encased in glass and buried underneath. So, the volume of waste generated by nuclear reactors is equal to 2 metric tons per reactor per year. So, there is no long-term storage site available in the US, and ever since the disaster in the 3 Mile Island of a nuclear power plant in the US, they did not build any more new power plants. So light nuclei can be combined. Light radioactive nuclei can be combined in a process known as nuclear fusion. So a hydrogen isotope can combine to form a beta particle and two positrons. Nuclear fusion is a very exothermic nuclear reaction. It releases as much as 2.5 times 10 to the 9 kilojoule per mole of energy. It is said that it is the energy source of stars. An attractive power source it is, because hydrogen as a fuel can be extracted from the oceans. And the waste products are short-lived and they are low mass isotopes. So fusion releases more energy than fission. It is the energy emitted by stars, which is said to contain mostly hydrogen, fusing to form helium. There is no safe way yet to harness fusion. So despite the great potential of the energy from fusion reaction, at present, there is no safe way yet to harness fusion, and it takes too much energy to get started. So commercial fusion reactors are not very likely to occur in the near future. So this is the end of our lesson on nuclear chemistry. I hope you appreciate the lessons that you learned from this.